Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 2nd, 2025, about 2 days ago. The striking result is that this paper finds xLSTM is strictly Pareto superior to transformers across roughly 5 orders of magnitude of training compute, and at a 16,000 token prefill, it delivers 30 to 50% lower time to first token. The paper is titled, xLSTM Scaling Laws, Competitive Performance with Linear Time Complexity. And as we'll see later, the implications for long context inference are quite significant. Beyond that, the study spans 672 training runs and maps compute optimal sizes, stable over-training behavior, and inference scaling using both IsoFLOP sweeps and a parametric loss fit. The introduction set the stakes for long context costs. Figure 1 shows validation loss versus training compute. The left panel plots the Pareto frontier, where xLSTM traces a consistently lower loss at the same flop budget, so for a fixed loss it needs fewer flops. The right panel presents a parametric fit that models loss as a function of model size and dataset size, which aligns with the empirical points across sizes and highlights stable advantages. Alright, Figure 1 established the performance gap. Figure 2 shows the full dataset of training runs, with model parameters on the vertical axis and training tokens on the horizontal axis. The left panel charts transformer runs, which form steeper IsoFLOP bands that spread as context grows, so longer contexts cut available tokens. The right panel charts xLSTM runs, where the IsoFLOP bands overlap more, which indicates linear scaling preserves tokens. The legend encodes context length by marker type and training compute by color. So Figure 2 highlighted how context length reshaped the training grid. Figure 3 shows validation loss versus compute on log scales for multiple tokens per parameter ratios, with separate panels for transformer and xLSTM. The mostly parallel fitted lines indicate constant ETA exponents, which means loss keeps improving predictably as compute rises, even when the data to parameter ratio is very large. That stability matters because small, inference-friendly models can still benefit from huge datasets. So the previous figure showed stable ETA exponents. Figure 4 analyzes compute optimal sizing under IsoFLOP budgets. The left panel plots validation loss versus model parameters with U-shaped profiles, and the minimum mark n star. xLSTM sits lower in loss, and its optimal size lands larger than the transformer at the same compute. The right panel fits n star versus compute with power laws, showing similar exponents, while xLSTM consistently prefers a bigger model. Well, Figure 4 analyzed compute optimal sizing. Figure 6 charts time to first token on the left and step time on the right versus prefill length from 1 to 16,000. Transformers rise sharply because attention scales with the square of the prefill, while xLSTM grows roughly linearly. At 16,000, time to first token is about 30 to 50% lower for xLSTM. Step time stays flat for xLSTM, yet grows for transformers. Alright, those runtime curves were clear. Table 1 lists the IsoFLOP training batch sizes at context length 8,192, which keeps total tokens per batch constant across compute budgets. Most budgets use 128 sequences, giving about 1.05 million tokens, while the largest budget at 6 times 10 to the 20 flops doubles to 256 sequences, about 2.1 million tokens. This consistency helps avoid loss offsets and keeps runs tractable. So, 2 takeaways stand out. xLSTM is Pareto superior across wide compute budgets, and its linear time design widens the gap as context grows, cutting time to first token by roughly a third to a half at long prefills. The implication is cheaper, faster, long context deployment without giving up accuracy. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.